Hi, my name's Melanie Finch and I'm from Monash University in Australia. Thank you for asking me to do this Tech Task talk. Today I'm going to be talking about the development of C-prime shear bands. This is work that I mainly did when I was on a postdoctoral fellowship at the University of Tübingen in Germany, and I was there on an Alexander von Humboldt postdoctoral fellowship. But prior to this work, I have worked quite a bit on naturally deformed rocks in ductile shear zones. And this is a thin section from one of the shear zones that I've worked in the Zanskar shear zone in the Northwest Himalaya. And you can see here that there are different domains within this rock that are deforming quite differently. This thin section came from this outcrop, and you can see here that we have these light and dark bands. So this rock is orthogneiss, and we have, the development of, sort of shear sense indicators. So there's Cplane here and S-plane there, so defining an SC fabric. And we also have these big C-prime shear bands in this orientation as well as many other shear sense indicators through there. So we took a sample of this rock and made a thin section that looks like this, and you can see those light and dark layers are replicated in this thin section. So the darker layers are these mica-rich regions, and we have a lot of biotite and a lot of muscovite. Muscovite has the high birefringence, and with the pinks and the greens forming these mica-fish here. And in the top region, it's really quartz and feldspar rich. And here you can see a feldspar grain that has a feldspar porphyroclast that has undergone brittle fracture, and the fractured pieces have been pulled apart from each other. So these two regions are forming quite differently from each other because the minerals in them have different strengths. Particularly in the mica-rich region down here, you can see the development of SC fabric. So C-planes are in this orientation, like through here. They're parallel to the shear zone boundary. S-planes are at an angle like this, in this sort of orientation. So SC planes define the shape of these mica-fish. And then we have C-prime planes, which dip down in the direction of shear. So down towards the right in this thin section. And you can see, if I take those away for a moment, you can see those C-prime planes are defined by these biotite-rich layers. So that's what's forming those mostly. And that they form quite commonly in this mica-rich region down here, but they're a lot less common in this quartzo-feldspathic part of the thin section up here. C-prime shear bands are also known in the literature as extensional crenulation cleavage. So if you've read about those before, we're talking about the same thing. Okay, so we understand pretty well how SC fabric forms. We've understood that for quite a long time, but C-prime planes have proven to be a little bit more enigmatic. So if we take this schematic sketch of how a shear zone develops and how SC fabric develops, we have just say the shear zone boundary like this, and then dextral shearing. The first thing to happen is that S-planes nucleate at an angle of about 45 degrees from the shear zone boundary. That's defined by the alignment of minerals, usually the weaker minerals within the rock. These S-planes rotate toward parallelism with the shear zone boundary with progressive shearing, and eventually become C-planes. And then all the time you can have new S-planes nucleating at the same time as these older ones are rotating towards the shear zone boundary. So that can form a fabric like this. This is a typical sort of asymmetry there, and we can see that all throughout this thin section. But yes, these C-prime shear bands are a lot less well understood. The work I'm going to tell you about today, I've published in this paper a few months ago in the Journal of Structural Geology. And there are my co-authors, most of whom are part of, all of whom are part of the Numerical modeling group there. So if you don't have access to Elsevier and you want to read this paper, you can email me, or you can get this author copy, which is an unformatted version of this paper on ResearchGate. The movies that accompany this paper are available in the supplementary material for this paper, or on YouTube. So you can, some of them are on the OWL YouTube page channel, and the rest are all on my YouTube. So freely available for you there. Previous research on C' shear bands in naturally deformed rocks has suggested that C' shear bands nucleate on the plane of maximum shear strain rate. They're thought to represent flow parallel to the shortening eigenvector due to bulk hardening or perhaps general shear. And it's also thought perhaps they form during the last stage of shear zone activity, and that's because they commonly cross-cut SC fabric or S planes. So it seems like, just from overprinting relationships, that they could be one of the last things to form, perhaps, yeah, due to hardening. These thin section pictures are from this paper by Gillum et al. In 2013. And you can see here that the micro-rich layers, again, are defining those C' shear bands. Experimental studies, of course, have the advantage that the starting material is constrained. And so you know the factors in the starting material that contribute to the development of structures after, during deformation. So these experimental studies have found that C' shear bands form when the strength ratio between minerals is at least 3 to 5. So what I mean by that is, if you start off with a rock like this, we have quartz and feldspar and mica. So the feldspar would be the strong phase and the mica would be the weak phase, and the ratio between them needs to be at least 3 to 5. So that's manipulated by changing the pressure and temperature conditions, so mainly the temperature conditions of the experiment, and that manipulates the strength ratio between the minerals. The proportion of the weak phase needs to be at least 20% for C' shear bands to form. That's what previous research has determined. So it seems like these two factors, the strength ratio between different minerals and the proportion of the weak phase, that they're really two important factors that determine whether or not C' shear bands form. So I decided to focus on those two factors and manipulate them to see how and why C' shear bands develop. So I used the numerical modeling platform L, and you can find out more about L at this website here. And I started off with a microstructure that looked like this, but with different proportions of the minerals. So in L, these grains are known as flins, and flins are defined by boundary nodes that are connected with straight lines that form these sort of polygonal shapes that define flins, which are grains. So you can see those boundary nodes there. And we also have this network of unconnected nodes behind the, well, not behind, but we have the network of unconnected U nodes here that store information about the strain rate and the stress, as well as the orientation of the orientation of the U node within the flin. So that's what enables us to determine the strain rate and the stress, or record that as the experiment proceeds. So very useful feature. Okay, so we started off with starting microstructure like this, and the way that L works is that you undergo one step of deformation, and some grains leave the right-hand side of the box, and then they're repositioned to the left-hand side. So we just have these wrapping boundaries like this. And we're using a full field viscoplastic deformation code. And if you want to know more about that, that's in the paper, and then in papers I cite in the paper as well. Okay, so the deformation is accommodated by dislocation glide on crystallographic slip systems. So just like minerals in nature have slip systems, and that slip on those slip systems, and that's how the rock deforms. The grains and the flins in L also have slip systems. And we're able to set the critical resolved shear stress of those slip systems in order to define the resistance to shear of the slip system. So basically that's the strength of the mineral. So we're able to define the strength of the minerals by manipulating or changing this critical resolved shear stress. So we're able to simulate a microstructure like this, or three-phase or microstructure like this, where we have very weak biotite, we have strong feldspar, and intermediate strength quartz. So that's what I did, using those three phases, those three minerals there, simulating the main features of each. So in grey, we have the strong phase, in black is the weak phase, and in white is the intermediate strength phase. In the experiments, I had 3 phase strength contrast levels: low, medium, and high. And what that meant is just the difference between the strength of the 3 phases. So in the low phase strength condition, the intermediate phase was 1.5 times the strength of the weak phase, and the medium phase strength contrast condition was 2.5 times, and high it was 4 times the strength of the weak phase. Because micas have an isotropy, and that's a really important feature of how they deform, we wanted to make a weak basal plane in the weak phase. So the basal plane was 1/10 the strength of the non-basal planes in mica. And then the strong phase was just double the strength of the intermediate strength phase. So those are the 3 phase strength contrast levels. And then we have 4 weak phase proportions. So 5, 15, 30, and 45% weak phase. So a 3x4 design gives us 12 conditions. We simulated Dextral simple shear in 900 steps, and each step involved a gamma of 0.02. So that, the finite strain increased with each step, like follows. And then we recorded the grain microstructure at each step. So that, for instance, by step 18, we had a gamma of 0.36, and by step 900, we had a gamma of 18, which was the maximum for each model. Okay, so now I'm going to show you some movies of the different microstructures. So in these movies I show, I'll have the proportion of weak phase up here. This is just to remind you that the strong phase is in grey, the weak phase is in black. This is the grain microstructure here, and then on the right hand side is the strain rate. So the strain rate's high where it's red, low where it's dark blue, and this up here I have the strength contrast between minerals. So this is a high phase strength contrast condition. So let's get underway. So you can see fairly early on that the minerals align to the S plane, and then layers of weak phase connect up, and then they rotate toward the C plane. So we've already got some C plane parallel layers through here. If you look over here, those C plane parallel layers are what have the regions that have the highest strain rate. So here's a high strain rate, here's a high strain rate. So these weak phase layers that are parallel to the C plane are really partitioning the strain rate in these models. The layers of weak phase slowly connect up with each other. And the way that they do this is that there's high stress at the interface of the weak phase layer and the strong and intermediate phase regions. So that high stress at the tips of the weak phase layers causes those weak phase layers to link up. And that's something that's been suggested in the literature before. You can see that here we start to develop a through-going shear plane that's localizing a lot of the strain rate, and that's defined by a layer of weak phase. There are some areas within the shear plane that do not have weak phase, and they are sort of areas of lower strain rate, and it would be high stress in that region too. We have the development of asymmetric folds in regions that neighbour these high stress parts of the model that form where, that really particularly form where layers of weak phase have just not quite linked up. So there's a high strain rate creating high stress in those regions in between where layers of weak phase have not yet linked up. You can see that these layers of weak phase, like here, they rotate forwards, so into an orientation like this, and these are C prime planes. This one looks like it's rotating backwards. So this one's rotating forwards here, and then you can see it defined here by the strain rate. That's the end of the model. Okay, so the C prime shear bands are defined by layers of weak phase, and we'll see more of those in the next model. So here we have 15% weak phase and a medium phase strength contrast. The start of the model is the same. In a way, the minerals align to the S orientation, and layers of weak phase rotate into parallelism with C. And again, they are partitioning or localizing a lot of strain through here, down here as well, a lot of strain rate. This is a medium phase strength contrast model. So you can see that the strong phase in grey retains a more equant shape for quite a long time. So, areas that are some areas where it's more deformed, and then other areas where it's able to retain its a more equant shape for longer. We have C prime planes forming here and another one up here. And if we watch these, they rotate. So this one, I'm not sure what, so that one looks like it's shortening internally and collapsing. So C prime shear bands sometimes shorten and collapse. They can fold. This one has folded. Yeah, that one looks like it's folded. You can see the fold defined in the layers around it. But other ones rotate backwards into parallelism with the C, so C plane. So these shear planes, C prime shear bands can rotate forwards and then rotate backwards. Here we have the development of a through-going shear plane that's partitioning almost all the strain rate. So not much else happens in this model because that just sort of carries on like that. So we'll move on to the next one. This model has 30% weak phase and a low phase strength contrast. The start of the model is quite similar to what we've seen previously. However, you can see these vertical areas of higher strain rate through here. They're sort of gone now. They don't last very long. They're just sort of at the start of the models, and mostly in the models with a higher proportion of weak phase. They accommodate rotation of lithons within the model, and you'll see those developed in the next model better than in this model, and those have an antithetic shear sense. So these are sort of like C double prime shear bands, but we'll see more of those in the next model. Again, in the 30% weak phase model, we do see the development of C prime shear bands. Here's one through here. And if you watch that, keep following that through, you'll be able to see the fate of that particular C prime shear band. It looks like it's getting thicker, so it's shortening and collapsing. There's another C prime shear band down the bottom here. It has also collapsed. Nice development of SC fabric in all the models, as well as these asymmetric folds are a common feature. It's interesting to watch. You can go back and watch just for fun. You can go back and watch the development of these asymmetric folds, and you can see how something like this forms with these two opposing noses. And that's from when asymmetric folds are sheared apart. They, can form a structure like that, which is pretty cool to, because I've seen that in outcrop, and it's cool to see it in the models as well and understand how it forms. Here's a C prime shear band through here, and that has collapsed. There's another one forming down here. one through here that's also undergoing shortening through here. So when you step through the model slowly, it's really easy to, well, it's easier to find these C prime shear bands. And if you watch them, then you can see them rotating back and forwards. And also with the movies, you know, you can go back in time and forward in time, and then you can sort of, yeah, either make yourself seasick or you can see the development also with other structures. This model has 45% weak phase. Here you can see those vertical shear bands that I was talking about before. They show a high strain rate. This is a lithon here. That lithon there is rotating. You can see that happening there. And that this vertical sort of shear band is accommodating that rotation. So in these models, those vertical shear bands form due to the rotation of lithons like that. This 45% weak phase model sort of forms a more anastomosing shear zone defined by the weak phase. There's a lot more weak phase. It allows, you know, that the shearing to sort of form that, yeah, anastomosing kind of shape. That lithon, is this one here. And I think that's another one there. And these slowly get sheared apart. You can see they've got a little bit of weak phase within them, and that allows them to sort of shear apart. We see C prime shear bands through the model, like there, that one just rotated backwards there. This one here is a C prime shear band, but they're a lot more ephemeral, so they're a lot shorter lived than in the other models. It seems, but because, the strain rate distribution is a lot more sort of dispersed over a number of different weak phase layers. Things develop quite quickly in these models, which means that, you know, we have relatively, so this is a C prime shear band that's rotating backwards. We have relatively fast rotation forwards and then rotation backwards of these C prime shear bands. So even though this model has a lot of weak phase and there's just a lot of places where strain can localize, you can see we still get the development of, we start to get the development of these through going shear planes that are parallel to the C plane. So you get the grains linking up there to form those through going shear planes. And then as that happens, more of the strain rate sort of partitions to those layers. So we end up with a really high strain rate, in layers like that that are linked up. Okay, so that's just 4 of the models. There are 12, and each one has the strain rate and the stress as well. So you're able to watch all of those at the same time. And it's really fun and informative for sort of your understanding of how these structures develop, and really great for students as well, I found. So be sure to check those out if you're interested. So now I just want to talk about the processes that allow C prime shear bands to form. I determined that there were 2 main processes. The first one is when there's high stress in a hard phase bridge. So you remember me talking about how these layers of weak phase start to link up, and but there can be these still intervening areas where there's still quite a bit of strong and intermediate strength phase in between these linked up segments of the shear band. So those areas you can see here are at high stress. And that's, you know, we often see asymmetric folds forming in the regions above and below those areas that are at high stress. So like this. So here we have an asymmetrical fold that's formed through here. Now, so, you know, we have shortening occurring here. And to accommodate that shortening and the differences in strain rate through here, other layers within the model need to rotate forwards. So this is one way that C prime shear bands form. It's through, you know, regions, when regions are at high stress in other parts of the model, folding can occur and shortening can occur, and that mechanically requires other layers within the model to rotate forwards. So that's what's happened here. This layer of weak phase here is rotated forwards, and then it later rotates backwards as well. So with forward rotation and then back rotation, between these steps of the model. The second process that can form C-prime shear bands in the models is when there's a strain rate increase. So there's an uneven distribution of strain rate in these layers of weak phase. So here you can see an area of red here, and then the rest of the layer of weak phase is at a lower strain rate. So what that means is kind of this area is moving faster, than these areas, and that can cause the areas at low strain rate to rotate forwards. So we have high strain rate here and here, and so this area needs to rotate forwards in order to accommodate the high strain rate in those neighbouring, those adjacent and connected layers of weak phase. So that happens, and this region here that was originally parallel to C rotates forwards until it forms a C-prime shear band, and then rotates backwards into parallelism with the C-plane again. So forward and then backwards. That's why we talk about these ephemeral C-prime shear bands. So you'll notice in the two processes I've described that C-prime shear bands form in layers of weak phase that are at a low strain rate. So they form due to, they form only in these layers that are at low strain rate. So this is in contrast to previous research that has suggested that they form when they're on layers of sort of high strain rate. So we find that the C-prime shear bands evolve or do not. The only time that they do not form is when there's a 5% weak phase and a low phase strength contrast. So I didn't show that model, but not much happens in it, so it's not a very exciting one. But when there's a medium and high phase strength contrast, C-prime shear bands do form in these 5% weak phase models. The C-prime shear bands form in all other models, and they're more common. There's more of them in these high phase strength contrast models, but they are shorter lived. So they rotate forwards and backwards or shorten internally, sort of quicker than what happens in the other models. So they're more ephemeral. So C-prime shear bands either rotate backwards and become C-planes again, like how I demonstrated just before, or they can shorten and collapse. And I showed you a few instances of this occurring in the models and we were watching the movies. But basically what happens is that you have this C-prime shear band, like in a rotation like this. It rotates forwards too much, and then it shortens, enters the shortening field, and shortens like this, and it can form these sorts of X structures, like this, from the shearing apart of that layer. So that's, a pretty cool thing to observe as well. So as I was saying before, in contrast to previous research, we do not find that C-prime shear bands localize or nucleate on the plane of maximum shear strain rate. They don't require general shear, they can form during simple shear. And they do not only form at the last stage of shear zone activity, and they only require 5% weak phase to form. So if there's a moderate, at least a moderate phase strength contrast. So I should note, that these are mechanical models. They don't take into account recrystallization and many other factors. So like hardening and weakening and things like that. So these are all factors that would have an impact on the development of these structures in nature, which may explain why the results of this study are different to those that have been done previously as well. So this is really just placing constraints on their mechanical development. So that's cool. So if you want to know more, please have a look at my paper. Happy to answer any questions via email, melanie.finch@monash.edu. It was on the first slide, so you can go back to the start of the video if you want. I'd love to hear your feedback on this work. Thanks very much.